Hello everyone, today's topic is the strict binary tree. In our last video, we have discussed about the what are the trees, what are its terminologies and what are its application, and little bit we have studied about the what are the binary trees. So today we are going to discuss about the strict binary trees. So let's start with this. Okay. So what are the strict binary trees? I will draw a binary tree. Okay, I will say that this is an example of a strict binary tree. How I can say that? Okay, what are these numbers? These numbers are zeros and 2. The definition for the strict binary trees will be this, that the trees which having the only either the zero number of the child or exactly the two number of childs are called the strict binary trees. If I take the example of this node has the two childs a. Okay, I will give the names to them a, b, c, d and the e. Okay, the A node having the two childs B and the C. Okay, satisfying the condition. If I talk about the node B, the B node having the two childs D and A. Okay, again satisfying this condition. If I come to the C, C doesn't have any further child, so it's 0. D and E both doesn't have any further child, so these are the satisfying this condition. So we can say that this is the example of strict binary tree. Okay, next. As similar to of the last video, we have discussed about the height versus nodes in the two cases. In both the cases, that if the height is given, then how to find the number of nodes. If the nodes are given, then how we can find the height. Similarly, in this also we are going to derive the formula for both the cases when the height is given and the nodes are given. Okay, case number 1. So our case number 1 is when if the height is given and we have to find the number of nodes. Height is given, find number of nodes. So how we can find the number of nodes? First of all, we will calculate maximum, then the minimum. Okay. For the maximum number of nodes, the formula will be 2 to the power n plus 1 minus 1. This formula will give the maximum number of nodes, and for the minimum number of nodes are 2n minus 1 plus 1. Okay, here's the formula is like this. When the height is given, then how we can find the maximum number of nodes? 2h plus 2 to the power h plus 1 minus 1, and for the minimum number of nodes to the 2h plus 1. This is the formula. Okay, now the case number 2. The case number 2 is when the nodes are given and we have to find the height of the tree. Okay, so how we can find that? We have to generate the formula for the maximum and for the minimum. So what the formula will be? For the maximum height, I will take it as h. The maximum height will be log to the base 2 n plus 1 minus 1. This formula will give the maximum height of a strict binary tree. Okay, and for the minimum, what's the formula is? H equals to n minus 1 divided by 2. Okay, n is the number of nodes and h is the height of the tree. With the help of this formula, we can easily calculate the maximum and the minimum height of our strict binary tree. I hope till here you are understanding well, and now let's move on further. Now now it's time for the internal and the external nodes. internal versus external node. For the strict binary trees, this concept is much easier than as compared to the binary tree. Okay, simply if I said you this is a binary tree. Okay, it is a example of a strict binary tree. Every node has its two child. Okay, so what's the formula will be? If I said if I let I be the number of internal nodes and E be the number of external nodes. Okay, so then the formula will be E equals to I plus 1. This will be the formula, or we can say the relation between the number of internal nodes and the number of external nodes in the case of strict binary trees. You can put the values and can check it is working or not, that how many number of internal nodes are there, 1, 2 and the 3. Okay, 3 plus 1 equals to 4. That's the E. What's the E represent here? E is the number of external node. You can say that 1, 2, 3 and the 4. Yes, we got the answer 4. I hope you remember our last video in which we have discussed what are the internal nodes and what are the external nodes. Yeah, the nodes which do not have their further child are known as the external nodes, and these are them. 1, 2, 3, 4. There are the such 4 nodes are there in this strict binary tree, which those who don't have their further child. Okay, next, now let's talk about the n array and the m array. Now let's move on to our next topic, n array tree. If I take the example of a 3 array tree, then how's the tree will look like? Okay, what's the term this 3 array tree mean? That a tree which have the number of nodes 0, 1, 2 or 3. The tree which have either the 0, 1, 2 or 3 number of childs or the nodes are called the 3 array tree. So this is the example of a 3 array tree, because this parent node has these 2 childs. Okay, this child and this node has a 3 further childs, and this node has 1 child, and this node has 1 child. So the tree which have the number of nodes having their 0 child or the 1 child or the 2 child and the 3 child are called the 3 array tree. Okay, this is also having the strict, there is also a strict 3 array tree, strict 3 array tree. So what is it? The tree which have only the 0 number of nodes or either the 3 number of nodes. Such a tree is called the strict 3 array tree. If I draw the example for this strict 3 array tree, it will look like this. So here it is. There is no any child which there is no any node which have 2 number of childs or the 1 number of child. No, in this tree we have this node which having the 2 childs. Okay, actually I should draw one more here. Okay, now it's good. Now it's a strict 3 array tree. Sorry. Okay, so this node having the 3 childs. Okay, and this node having further 3 childs, this have further 3 childs, and this node further do not have any child, so satisfying this condition. Okay, so this is the example of strict 3 array tree. For this also we are going to calculate the maximum number of nodes, and these two cases, when the height is given and we have to find the nodes, when the nodes are given and we have to find the height. So let's start with the case number 1. When the nodes are given and the height have to find. So what's the formula will be? I am writing on this only. Okay. Yeah. What will be the formula when the nodes are given and we have to find the maximum height of the tree? Then the formula will become the n minus 1 upon m. Okay, and for the minimum height, the formula will be log to the base m n minus 1 minus 1. Okay, plus 1. This will become the formula for the maximum height. And similarly, case number 2, when height is given and we have to find number of nodes. Okay, maximum and the minimum. What's the formula will be? For the minimum number of nodes, the formula will be 3h plus 1, and for the maximum number of nodes, the formula will be 6h plus 1. Okay, you can put the value of the h and find the number of nodes. Here the number of nodes are 2, 4, 6, 7, 8, 9 and the 10. Okay, you can simply just put the value and you will get the formula for the maximum number of nodes. Okay, next let's move to our next topic, representation of a binary tree. Representation of a binary tree. We can represent a binary tree in the two ways. First is like an array and second is like the linked list. First of all, we will talk about the array. How we can represent a binary tree in the form of the array? Okay, first of all we have to take one array and let's make it A, B, C, D, E and F. One more I am taking G. The very first and the very important thing is there, we will start doing the indexing of this array with the 1, not with the 0. Okay, that's the major thing here. So I am doing the indexing of this array with the 1, 2, 3, 4, 5, 6 and the 7. Here is my arrays. So if I draw a particular table for this, the first of all I would like to tell you about that the left child and the right child. If I ask you to tell me about the left and the right child of this array of the array element A, then what will you tell? The left child of this element A is B and the right child of this element A is C. Is the left child and this is the right child. Okay, similarly for all the respective elements I am going to make a table, then we will also derive the formula for this which we will use further. Okay, for two or the 3 elements I am doing it manually and then we are going to derive the formula for this. Here I am putting the elements as the index represented by I, and is the left child and the right child. Okay, I hope board is visible to there also. Yeah, so the elements of our array are A, B, C, D, E and F. Okay, G also is there. Yeah, so what's the indexing of these elements? A is at 1, 2, 3, 4, 5, 6 and the 7. Okay, so who is the left child of this element A? Yeah, B. B is the right child. The left child is B. Okay, I will write it with the red pen. B. B is the left child. Okay, then who is the right child? The C. C is the right child of A. We have completed with the A. Now the B. Who is the left child of this B? Left child of this B. D. The left child of the B is D. And who is the right child? Yeah, absolutely. The right child of this B is E. Okay. Similarly, if I want to derive the formula for this, what I think you should also notice one thing, that the left child and the right child with the parent node have some relation. That if I take this example, okay, A, it is at the index 1. It is at the index 1. So who's the right child? This one. Okay. If I said I is the index of these element, so the formula will be 2 into my I. You can check. Okay, for the right child, for the left child, this is formula for the left child of these element. Okay, A, if we talk about the A is at the index 1, so simply just put the value 1, so 2 1s are 2. So at the element at the indexing 2, who is the element will be the left child of this element A. So B is the left child. Okay, next you can check for the B. B is at the index 2 and 2 2s are 4. Okay, so at the fourth index, who's the element? D, and the D is the left child of B. I think you got it. Now let's come to the right child. As simple as we can see that also, if the B is the left child and its next position element is the right child for the parent node, so the formula will be 2i plus 1. Yeah, as simple as the formula will be 2i plus 1. You can again just simply put the value of I and can check. Okay, A is at the index 1, put the value 2 1s are 2, 2 plus 1 3. Yeah, C is at the index 3, so C become the right child of this A. For the B, similarly we will put the value 2, 2 is a 4, 4 plus 1 5. At the index 5, who is the element? E, so E become the right child of the parent B. Similarly, we can calculate all the left and the right child for all the n number of the elements of this array. We don't need to always calculate manually. We can just simply put the value of the index, okay, and then find the element who is the left child and the right child. Okay, now let's come to the linked list. We are done with the array. What we have seen that the representation of the binary can be done in the two ways, array and the linked list. With the array we have studied about this, and now we are going to study about the linked list, how we can represent a binary in the form of linked list. if I said that this is a binary tree which I am making and I have to represent it in the form of linked list, then how I am going to make this out? Let's see here. It's the root node. It's our root node. First of all I am drawing all the nodes here, then we will just link all them together. Okay, yeah. A, B, C, D, E, F and the G. What the elements we have taken for the array, I am taking these all the same for the linked list also, A, B, C, D, E and F, G. Okay, so here's our linked list representation. Then how we are connecting this, the left child with the left node and the right with the right child. Okay, and similarly keep the linked list, the trees keep going on. And one thing you know about that, the further these external nodes have the null, these nodes are the null. Okay, we will say them the external nodes. As in the binary tree, what are the external nodes? The nodes which do not have their further child, and similarly these nodes do not have their further child. So I am telling about I am naming them as the external nodes, as these are my external nodes. So what's the formula for the total number of, if I want to calculate the number of external nodes in a particular linked list tree representation, then how I can calculate it? Yeah, let's have a look. For the formula, the formula will be n plus 1. And how it is came? Yeah, see there, how many total number of nodes are there in this representation? 1, 2, 3, 4, 5, 6 and the 7. The value of n is 7. N is 7. So simply just put the value n equals to 7 here. So this is a formula for the total number of external nodes. Okay, total number of external nodes. So when we put the value of 7 here, then the 7 plus 1 equals to 8. I am getting the 8. Let's check here, verify here. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I am getting the correct answer, that in this representation I am getting the total 8 number of external nodes here. Okay, so this is the representation of the binary tree in the linked list form. So let's move further. Types of binary. So the types of the binary trees are, yeah, full and the complete. What does it mean? What is the difference between the full binary tree and a complete binary tree? Let's have a look. Full binary tree is like that, for a particular height, if there are the maximum number of nodes are present, then the tree is termed as the full binary tree. I am writing it down. For a particular height, if the maximum number of nodes are present, then the tree is termed as full binary tree. Okay, I'll draw a tree, then I will explain. So here's the example of the full binary tree, that at a particular height, at every particular level of the height, there are the maximum number of nodes are present. Okay, at the root node, if they move to the first level, first height, then what's their number of nodes are present are 2. So in a binary tree, there are the maximum number of nodes are present can be 2 only. So here the maximum number of nodes are already present. At the next level, what's the level? 2. At the level 2, this child having this node having the 2 childs, and this node having the further 2 childs, and so this at this height also the maximum number of nodes are present. So this is the example of the full binary tree. Okay, and we already know what's the formula for the maximum number of nodes. Yeah, it is the to the power n plus 1 minus 1. This is the formula we have already discussed in our video lecture number 1. Okay, so next, now it's time for the complete binary tree. What is this complete binary tree? Any binary tree which having their left child compulsorily is known as the complete binary tree. Yeah, once again, yeah, the tree in which the every node having its left child compulsory is called the complete binary tree. This is the example of the complete binary tree, that because every node having its left child. Okay, you can draw it like this also. This is also an example of complete binary tree. Okay, so these are the types of the binary tree, full and the complete. We have studied about them. Okay, and next we are moving to the next topic of today's class, that what are the operations which can we perform on these binary trees. As when we studied the arrays, linked list, queues, stack, all these concepts, we have performed so many arithmetic logical operations on this. And so what are the operations which can be performed in the trees also? We are going to discuss about them. So what are the first of all, first operation which we can perform is, yeah, insertion, and the second one is deletion, third one is searching, fourth one is auxiliary operations, okay. And in these auxiliary operations, what are the things we can do? We can find the size of the tree, we can find the height of the tree, okay. We can find the maximum element, and then what we can do, then the last one is LCA. What does LCA mean? Least common ancestor, please don't mind my writing. Okay, these are some of the basic operations which we can perform on the binary tree. We can insert any new node in a binary tree if we want to, and the tree is allowing us, we can insert a new node. If we want to delete a particular node from a binary tree, we can delete also. If we want to search any particular node for the particular data in a binary tree, we can do it with the help of searching. So there are some of the auxiliary operations which are present in there, which include the finding the size of the tree, finding the height of the tree, least common ancestor, maximum element of the binary tree. These all are the operations which we are going to discuss about them in our next upcoming video. So I hope you understand today's lecture, and If there is any doubt, please you can mention after the video. Okay, I hope you are enjoying this series. Thank you.